Welcome to another section with me, Srilekha, lecturer in Mechanical Engineering, SRRS Government Polytechnic, Sirsila Agraharam, uh, Telangana. In the last few classes, we have been discussing how to solve the problems on simple stresses and strains, and also how to solve the problems for the given data of a tensile test. So, till yesterday, we have found various the th- factors such as the ultimate stress, tensile stress, and at the elastic constant, the modulus of elasticity, and then yield stress and breaking stress, working stress, actual working stress, and nominal stress, and percentage of elongation and percentage of reduction. In today's class, we are going to discuss uh, so one more case of these simple stresses. So how do you analyze the bars of varying cross section? Yesterday we have taken a single bar of certain cross-sectional area A, and we found simply stress and strain and then modulus of elasticity. So in that case, simply the stress was load by area, and strain was change elongation in length by original length, or change in length by original length. Then modulus of elasticity was stress by strain. So in today's topic we are going to take two or more bars of varying cross section. Say something like which we get by making use of step turning. Say if any objects formed by means of step turning, how would you analyze the stress and strain in such kind of specimens? So that we are going to discuss today. So today's contents are, so analysis of bars of varying cross section. It means of either decreasing or increasing diameter. That is something like the pieces obtained by making use of step turning operation. Next is bars of varying load. So initially it would be like the diameters are changing and the load is constant everywhere. In the next case, if the loads are changing. Then one more thing is the problems based on these types of bars. Okay, so let us start now. So for initially we are going to explain the various steps involved in analyzing the bars of varying cross section. So here a figure is given, that is 1.13. So in which you can see uh, in a composite bar, so two cross sectional areas are there. So it is D1 and D2. So there are two sections in a given bar. So let us consider a bar which is subjected to a tensile load P, and this bar is turned down to a smaller section over a part of its length. So initially let its diameter be a D2, be the maximum diameter, and let its diameter be a D1. So when you are applying certain tensile load, what happens? Its length will increase, that is this workpiece will elongate and its diameter will be decreasing. So that is why reduction in the area occurs and elongation in the length occurs. Now, so the total change in the length of this specimen. So how you are going to calculate the total elongation in the length. So here if you see, the bars are of varying cross section but not varying loads. So the load is constant here. And if you see, we know that so the stress in the narrow section will be higher than that of stress in the narrow portion, it will be higher than a broader portion. And we know that uh, modulus of elasticity or Young's modulus is equal to stress by strain. So if I write strain as the subject, then strain is equal to stress by modulus of elasticity. So this modulus of elasticity is different for different materials. Say here if I am taking some steel and some cast iron, then for steel it is 2 into 10 to the power of 5. So for cast iron it is something different. So this value is not constant for both the materials. Okay. So next, say if this for this section 1 the stress is P by A1 because D1 is the diameter. So it's, let us consider its area B, corresponding area B A1, that is pi by 4 D1 square. Similarly for this, so P is the load and its area B uh, A2. A2 is pi by 4 D2 square. Now, so how do you calculate the total elongation? So stress you will be taking simply P by A1 and P by A2. Next, strain is Young's modulus is E as it is. Now strain is equal to P by A into E. So P by A1 into E1 plus P by A2 into E2 if it is a different material. So let us see the next one. So in this manner. For the first section, I am taking stress is equal to load by area of that first section. So sigma is equal to P by A1. So sigma 1 equal to P by A1. Next, elongation. Elongation is nothing but change in length. So how can you get this elongation? So we know that strain is equal to elongation by length. Now, if I take E value, so modulus of elasticity is stress by strain. Then strain is equal to stress by modulus of elasticity. So this strain is nothing but change in length by original length. Then change in length is equal to stress by strain into original length. So as simple as it is. Simply we are making use of modulus of elasticity is equal to stress by strain formula, and instead of strain E we are just substituting delta L1 by L1. So since this is a first section, so simply P L1 by A1 E. Okay. Since sigma is P by A, sigma 1 equal to P by A1. So L1 by E1. So P L1 by A1 equal to A1 E is the elongation in first section. So similarly, if you take second section, so in the second section also, stress is simply sigma 2 equal to P by A2. That is, stress is equal to load by area of the section 2. Next, elongation in length. Similarly, like that only. So we know that strain is equal to stress by modulus of elasticity. So in the assumptions itself we have taken. So strain is nothing but change in length by original length. So therefore this is nothing but change in length is equal to stress by modulus of elasticity into original length we have taken. So this one it is taken directly instead of 2-3 steps, directly they have written elongation in length is equal to stress by modulus of elasticity into original length. So instead of stress we are substituting P by A2. So therefore the entire formula becomes PL2 by A2E. Now total elongation of the specimen of the bar is delta L is equal to, so elongation under section 1 plus elongation at the section 2. So elongation in section 1 is PL1 by A1E plus PL2 by A2E. So here the load and the load is same. So we have told that uniform load, it is not a varying load. So P is same everywhere. And also if the material is same for both the sections, then E value is also same. So P by E into L1 by A1 plus L2 by A2. So here P is the tensile load that is acting on the bar. E is the Young's modulus. Next L1 is length of the section 1. A1 is area of the section 1, cross sectional area of the section 1. Next L2 is length of the section 2. A2 is area of cross section of the section 2. So in this manner we are going to find total elongation of the specimen for a uniformly varying cross sectional area specimens. So let us do few problems on that. Now see, if this, so here in the previous case we have taken the same load, that is P everywhere same. Now if the bar is subjected to varying loads, it means, so in the first section if it is having some P1, in the second section it is having P2, then how can we take? So if when the bars may be subjected to loads varying from portion to portion, in such cases the load acting in each portion may be found and elongation of each portion under respective load may be calculated. The total elongation will be sum of the algebraic individual elongation. So if it is a varying load, so I'll go to the back one. So if it is a varying load, means the P value is not constant. So in the section 1, if load is P1 say, then here it will be elongation is P1 L1 by A1 E, and then elongation at the second section will be P2 L2 by A2 E. So therefore the total elongation will become like 1 by E into P1 L1 by A1 plus P2 L2 by A2. So if the load is a varying one, we have to take 1 by E into P1 L1 by A1 plus P2 L2 by A2. So likewise we will be calculating the solutions. Okay. So for the varying loads. Next. So let us do a problem. Now see, a steel tie rod of 40 mm diameter and 2 mm long is subjected to a pull of 80 kilonewtons. So to what length the bar should be bored centrally so that the total extension will be increasing by 20% under the same pull. So the bore being 20 mm dia. Take ES is equal to 2 into 10 to the power of 5 Newton per mm square. So it is given that a steel tie rod which is of 40 mm dia and its length is 2000 and it is subjected to an axial load of 80 kilonewtons. So it is a tensile load of 80 kilonewtons. Now if I bore, I mean if I make a hole, so boring is nothing but making of a deep hole. So if I do some boring centrally at this center, so that its extension will be increased by 20% under the same pull. It means so that its change in length will increase by 20% under the same pull, and this hole, I mean this bore, it will be of a diameter 20 mm. Now, so now I have to find the length of that bar. Okay, so I have to find the length of that bore. So how much up to what length I am going to make the hole. Okay, so once again I am repeating. So if a steel tie rod which is 40 mm dia and it is 2 meter long, nothing but 2000 mm length, and it is subjected to a pull of 80 kilonewtons, nothing but to a tensile load of 80 kilonewtons. Now the question is, to what extent the hole is to be made. A boring operation has to be made centrally. It means like this. Made so that its total extension will increase by 20% with the same pull, that is with same 80 kilonewtons. So how it will increase by 20%. Okay, so here modulus of elasticity is given, that is 2 into 10 to the power of 5 Newton per mm square. Okay, so how we'll be calculating? So with the given data we have to find first the uh, change in the length, that is total extension. Then to that total extension, by making use of this condition, that is nothing but total extension is increasing by 20%. So now the next extension would be 1.2 into the delta L. So with that, by making use of that, we have to find L value. Okay, so let us do this. So given that diameter of the rod is 40 mm. Now the area of cross section we know that. So it is a circular cross section one bar. So its area of cross section will be pi d square by 4. Now so d value is 40 mm. So just substituting 40 in place of d. So you will get a value of 400 pi mm square. Okay, now next, so stress induced. So stress is nothing but load by area. So stress induced initially is sigma 1 is equal to load by area of the specimen, that is nothing but 80 into 10 to the power of 3 by 400 pi. So if you calculate this, you will get a value of 63.66. Okay, now extension of the rod means, so initially we have to take the extension of the rod. Extension of the rod means nothing but change in the length. So change in the length, how can we find? Already we have discussed earlier. So modulus of elasticity is equal to stress by strain. Now strain is equal to modulus of elasticity, stress by modulus of elasticity. Now instead of strain we are going to write change in length by original length. So change in length or elongation of the length is equal to stress by modulus of elasticity into original length. So stress we have found now, that is nothing but 63.66 into 2000 is nothing but length of the specimen by E value is already given, that is 2 into 10 to the power of 5. Now on substituting all the values, you will get 0.637 mm. It means the solid rod which was given, the tie rod, steel tie rod, which is of 2000 mm length and so for 40 mm diameter. So when you are pulling it with 80 kilonewtons, you will be getting this much of extension. Now if I take the body with the bore, it means, see, if I am making this hole of diameter 20, okay, Now the extension is, so extension was given that it will be increasing by 20%. So initially it was 100, 1. Now 20% means 0.2. So 1 plus 0.2 is nothing but 1.2. Now after making this whole, the extension will be 1.2 into original one. So 1.2 into original one means 1.2 into 0.637. Now it is nothing but 0.7644 mm. Now if I take bore diameter, so bore diameter is also given. It is 20 mm. So cross sectional area means, see, this is the hole. Now the remaining material you have to consider. So the remaining material is what? Nothing but pi by 4 d square minus this d square. So the leftover thing is simply pi by 4 into 40 square minus 20 square. So this is a gap. The material which is there only you need to consider. So we have considered that you will get a value of 300 pi mm square. Now stress induced is simply sigma 2, stress is equal to load by area. What is the load? So the load is same. It is given that the load is not going to change. It is 80 into 10 to the power of 3 by 300 pi. So 300 pi is the area that we got after we have made the bore. So this value is 84.92. Okay. So 84.92 is the actual stress induced if you are going to make a bore. Okay. Now length of the bore you need to find. So length of the bore is how much? So to find length of the bore we need to get, we are given with the extension, nothing but change in the length. So that change in the length will help us. We know that change in the length is equal to, so sigma 1 L1 by E1 plus sigma 2 L2 by E2. So sigma 1 L1 by E1 is nothing but, so sigma 1 is already given, that is 63.66. So L1 means this length we want. So for this piece means for this box, so where the diameter is 40. So for that box it is sigma 1 E1 into, so this length is how much? 2000 minus L. So 2000 minus L we are taking plus this, for this, so we have to consider only this area because this is a hole. So this area is how much? This stress is how much? 84.92 into length we are not known, that is L. It is simply L and by E2. E2 is nothing but modulus of elasticity 2. So for both the modulus of elasticity is same, but we are taking E1 and E2, no problem. So the change in length or extension in length is there, that is 0.74644 is equal to the sigma 1 value is there, that is 63 point something, and sigma 2 into 2000 minus L plus 84 into L by 2 into 10 to the power of 5. So if you are substituting all the values, you will get L, one positive and one negative, and the positive value you have to consider, that is nothing but 1202. Okay. So 1202 mm of length of bore you are going to make. Okay. So this is going to happen. Now, so once again let us see. So a steel tie rod of 40 diameter and 2000 length is given, and the load is 80 kilonewtons. So without changing its pull and increasing its elongation by 20%, so what would be the length of the hole that is made, length of the bore that is made. So for this, what we have done is, so initially we considered this bar and we found change in length. Okay, so change in the length we have considered. Thereafter, it is given that extension is increasing by 20%. So when the extension is increasing by 20%, by considering that 1.2 into change in the length we have done, and we found that extension again. Now next, by making use of that elongation, we know that elongation formula for varying bars, that is nothing but sigma 1 L1 by E1 plus sigma 2 L2 by E2. So we used a sigma 1 value, sigma 2 value, and we have calculated that L which is left over. So that was the thing which we have done. Now next, so a copper bar 250 long is 30 in diameter for 150 of length, and 20 diameter for the remainder. Okay. A tensile load is supplied to the bar so that the maximum stress induced in the material is 50 Newton per square. Now determine the magnitude of the load and calculate the total extension of the rod. So for copper, E is equal to 1.03 into 10 to the power of 5 Newton per square. So I think understood. So a copper wire is there, that is of 250 length. So its diameter is 30 for 150. So for that, in the entire 250 so 150 length is 30 diameter, and the remaining 100 is 20 diameter. It is a stepped bar, something like a stepped bar. Okay. So now it is given that the stress induced in the material is 50 Newton per square. Now we need to find the load acting P and the total extension of the rod. Okay. So let us find the solution. Okay. So given, so this bar is of 250 length, but so 150 length is of 30 diameter, and remaining 100 is 20 diameter. Okay. So diameter of the smaller section D1 is equal to 20 Now D2 is equal to, so by D2 is equal to 30 So D1 is there. So therefore its corresponding area A1 is equal to 5 by 4 D1 square. So if it is 5 by 4 D1 square, then I will simply substitute 20 there. So the answer would be 100 pi. Okay. So 4 ones are 400. Okay. Next, diameter of this larger section is 30 mm. Now, area of this larger section will be pi by 4 into 30 square. Next, given Young's modulus is 1.03 into 10 to the power of 5. Now, maximum stress induced in the body at the smaller section is sigma 1. It is nothing but how much? 50 Newton per mm square. Now, load is nothing but, so how can you find load? Load is simply, so stress is equal to load by area. Now, load is equal to stress into area. So, maximum stress 50 into area is 100 pi. So 100 pi we got. So 100 pi into 50 is 15.7 kilonewtons. Okay. Next. So total elongation in length. How much? So total elongation in length is PL by P by E into L1 A1 plus L2 by A2. So it is P value is 15.7 into 10 to the power of 3 by E value is 1.03 into 10 to the power of 5 into 100 by 100 pi plus 150 by 225 pi. So that will give us 0.08 mm. Okay. So this is how we find the value. Next. So a circular bar which is shown in the figure is subjected to a tensile load of 150 kilonewtons. So what must be the diameter of the middle portion if the stress induced there is 215 newtons, and also find the total extension of the bar. Now take E value is equal to 2.06 into 10 to the power of 5 Newton per mm square. Okay. So let us do this. So given that this is a circular bar which is subjected to a tensile load of 150 kilonewtons. So the load is 150 kilonewtons, and the stress induced is 215 Newton per mm square. Now we need to find this diameter as well as the total extension of the bar. Okay. So given load is 150, P is to 150. Now D1 is 50. So area of that is simply pi by 4 into D square. Okay. So pi by 4 into 50 square. Next, so load is 150 kilonewtons. So 150 into 10 to the power of 3 newtons we are taking. Next, so stress induced in the middle is given, that is nothing but 250 Newton per mm square. So area of the middle portion. So we know that stress is equal to load by area. Now area is equal to load by stress. Okay. So the load is 150 into 10 to the power of 3. So from this area A is equal to 697.67. But we know that area formula is simply pi by 4 d square. So instead of pi by 4 d square, I am taking, so d is equal to under root into 4 by pi. So just substituted the values there. Now, so d value is simply 29.28. Okay. So diameter of this portion d1 is equal to 29.28. We know that diameter of both ends is 50 mm. Now area of that end is pi into 50 square by 4, pi d square by 4, nothing but 1962. 1962.5. Next, so total elongation in the length. So we know that total elongation in the length is simply sum of the elongations at the sections. So here sum of the elongations at the sections means you have to take, here we have on both the ends, the here we are having three sections. So two sections of higher dia and one section is of less dia. Okay. Now higher dia section is simply we have taken two times of that, both the sides. Okay. So it is PL1 by A1E plus 2 into PL2 by A2E. Okay. So instead of P we are substituting 150 into 10 to the power of 3. So L1 is 160 and L2 is 45 and 45 on both the sides. So simply 2 into 45 and L3, so A1 is 697.67 and A2 is 1962.5. So on substituting everything we'll get simply 0.206. Okay. So this is how we'll do the problem. Okay. So a small confusion will arise while finding the total elongation. So that has to be kept in mind in better way. So you have to take their corresponding lengths and corresponding areas only. So if it is given delta 1 equal to delta L1 plus delta L2, then P L1 by A1E and P L2 by A2E you have to take. Okay. So in this manner you are going to do the problem. Okay. So once again let us discuss once the method of doing that. Okay. So that we will remember it in a better fashion. So when the bars are given of varying cross section, it means of the different diameters. So what we do here, when consider a bar which is subjected to the tensile load. And so we know that stress is greater in the narrow position. Okay. So stress is greater in the narrow position of the bar. Now we know that modulus of elasticity is equal to stress by strain. Now if I am considering strain, then it is simply stress by modulus of elasticity. So where E is nothing but modulus of elasticity. Now while finding these values, we will simply take, so initially for the first piece, so for this stress sigma 1 is P by A1. nothing but load by area of the first. So A1 how will you get? Pi d square by 4 will do. Next, so so this is sigma 1 is P by A1. Next, change in the length, modulus of elasticity is sigma 1 by E1. Now E1 equal to sigma 1 by modulus of elasticity. So let us see this. So stress in the first piece is P by A1. Next, elongation is got by the formula modulus of elasticity. How will you get that? It is simply stress by modulus of elasticity into original length. So instead of stress, we have written P by A1. So P L1 by A1 E. Next, if I am considering second section, here stress is equal to P by A2. Next, elongation in length is simply P2 by A2. Now total elongation is simply sum of the elongations that we are going to take is nothing but P1 L1 by A1 E plus PL2 by A2 E. So PL2 by A2 E. Say here the load is same, only the areas are changing. Now if I take different loads, varying loads, then it is simply will take P1 L1 by A1 E and plus P2 L2 by A2 E. So if it is a varying load on P1 L1 by A1 E plus P2 L2 by A2 E. So this is how we calculate the total elongation for uniform varying cross sections and the varying loads. Okay. So in the next class we will be discussing about the thermal stresses and strains. Okay. So how the thermal stresses are induced in the body and how can we calculate them. So all this we will be discussing in the next class. And for today you just practice this for the uniformly varying bars, and from the next class we will be discussing the next cases, that is thermal stresses. Then after composite bars, likewise we have many types, so we will be discussing everything. Okay, thank you.